Somewhere out there, hidden in the vast darkness between stars, an invisible force holds entire galaxies together like cosmic glue. You can't see it, you can't touch it, but without it, the universe as we know it would fly apart. This is dark matter, the universe's best-kept secret, and it's just one of the countless mysteries lurking beyond the edges of human understanding. What if everything we think we know about reality is just the tip of the iceberg? Picture this: a single teaspoon of empty space isn't empty at all. Quantum physics tells us it's a seething, bubbling ocean of energy particles flickering in and out of existence so fast we'll never catch them. And what if those fleeting particles are whispering the secrets of dimensions we can't even comprehend? Some scientists believe our universe might be floating like a bubble in a higher dimensional sea, bumping against realities we can't see. These aren't just wild fantasies, they're real theories from the brightest minds in physics, each one unraveling another thread in the fabric of the cosmos. That's what we're diving into today, 30 of the most astonishing theories about the hidden forces shaping our universe. From the eerie pull of dark energy expanding the cosmos at breakneck speed to the possibility that gravity itself might be leaking into our world from another dimension, these ideas will bend your perception of reality. Some might sound like science fiction until you realize the math checks out. So if you've ever stared up at the night sky and wondered what's really out there, you're in the right place. Because by the time we're done, you'll never look at the universe the same way again. What looks like empty space is anything but. Even in the deepest void between galaxies, the fabric of reality is alive with activity, a quantum frenzy so intense it defies our everyday intuition. At the tiniest scales, particles and their mirror opposites, antiparticles, constantly flicker into existence, only to annihilate each other in bursts of energy almost too fast to measure. These aren't just mathematical quirks, they've been caught in action. Take the Casimir effect. Place two metal plates incredibly close together in a vacuum, and they're inexplicably pulled toward each other. Why? Because the space between them is too narrow for certain quantum fluctuations to fit, creating an imbalance. Outside the plates, the particle-antiparticle dance continues unchecked, pushing them together with measurable force. This same omnipresent energy might hold the key to one of cosmology's biggest puzzles: why the universe is expanding faster and faster. Einstein once introduced the cosmological constant, a sort of anti-gravity force, to balance his equations, then dismissed it as his greatest blunder. But today, scientists suspect he might have been onto something. What if this quantum vacuum energy, this infinite sea of microscopic chaos, is actually driving galaxies apart? The math suggests that even if we could harness every star, planet, and speck of dust in the cosmos, it would amount to less than 5% of what's really out there. The rest, dark energy likely born from the same quantum froth we see in lab experiments, but operating on a scale so vast it reshapes the fate of the universe itself. Yet here's the twist: according to quantum theory, the energy density of empty space should be astronomically higher than what we observe. Some physicists argue this discrepancy hints at undiscovered physics, perhaps extra dimensions siphoning off the excess, or a flaw in our understanding of gravity. Others propose that multiple universes with different vacuum energies exist, and we simply inhabit one where the numbers allow galaxies and life to form. Whatever the answer, one thing is certain: the nothingness around us is the most vibrant something we've ever tried to understand. While dark energy pushes the cosmos apart, an even stranger cosmic architect holds it together: dark matter, the universe's invisible scaffolding. Imagine a spiderweb so fine you can't see it, yet strong enough to catch entire galaxies in its threads. We know it's there because stars at the edges of spiral galaxies rotate far faster than they should, like a merry-go-round spinning so violently that the children clinging to its outer edges would be flung off. But they aren't. Something unseen, something with gravity but no light, keeps them anchored. That something makes up roughly 85% of all matter in the universe, and we've never directly touched it. The quest to unmask this phantom has spawned two leading theories, each with its own tantalizing clues. The first pins hopes on WIMP weakly interacting massive particles. Picture these as cosmic ghosts, massive enough to bend space with their gravity, but so aloof they rarely bump into ordinary matter. To catch them, scientists have built ultra-sensitive detectors deep underground, shielded from cosmic noise by miles of rock. Laboratories like Italy's Gran Sasso or South Dakota's Sanford Lab monitor vats of liquid xenon, waiting for the faintest shudder, a WIMP striking an atom like a single snowflake hitting a piano string. Decades in, the detectors remain eerily quiet. Either WIMP are even more elusive than predicted, or we're searching for the wrong spectre. Enter the underdog actions. These hypothetical particles, lighter than a feather's shadow, were originally dreamed up to solve a puzzle in quantum physics. Unlike WIMP, actions wouldn't ignore ordinary matter. They'd metamorphose in the presence of magnetic fields. Experiments like the Action Dark Matter experiment use powerful magnets to coax these shy particles into revealing themselves as fleeting flashes of microwave light. The twist: if actions exist, they might not just be dark matter, they could be cosmic chameleons, shifting forms as they traverse stars or even Earth's own magnetic field. The stakes couldn't be higher. Finding WIMP would mean dark matter is a relic from the universe's fiery birth, a heavyweight survivor of the Big Bang. Actions, though, would rewrite the rules of dark matter so delicate it dances on quantum strings we've yet to pluck. And if both searches come up empty, that's when things get truly wild. Some theorists suggest dark matter isn't particles at all, but primordial black holes left over from the universe's first second. Others whisper of entire shadow galaxies, parallel worlds of dark atoms interacting only through gravity. One thing's certain: every flicker of data, every unexplained blip in these experiments pulls us closer to rewriting the story of the cosmos. Because dark matter isn't just hiding in the shadows, it's the hidden hand shaping everything we see. If dark matter is the cosmic glue holding galaxies together, dark energy is the unseen hand ripping them apart at the seams, an anti-gravity so powerful it's stretching the very fabric of space. The discovery of this force shocked the scientific community so profoundly it earned the 2011 Nobel Prize in Physics. Here's how it happened. Astronomers were measuring distant supernova, the explosive deaths of massive stars, expecting to find the universe's expansion slowing down under gravity's pull. Instead, they found the opposite. The light from these dying stars was fainter than it should be, meaning space itself had stretched more than predicted since the explosions occurred. The universe wasn't just expanding, it was accelerating, as if some invisible pedal was pressed to the cosmic floor. Two leading theories attempt to explain this bizarre repulsion. The first resurrects Einstein's old cosmological constant, the energy of empty space itself. Picture a balloon inflating. As space grows, more vacuum appears, and with it, more of this mysterious energy pushing outward. But there's a catch. Quantum physics predicts the vacuum's energy should be 10 to the power of 120 times stronger than what we observe. That's a 1 followed by 120 zeros, enough to tear atoms apart instantly. If the numbers are so catastrophically wrong, why does the cosmological constant fit observations at all? Some suggest an unfathomable fine-tuning. Our universe's vacuum energy is perfectly balanced on a knife's edge, allowing galaxies and us to exist. Enter quintessence, a dynamic alternative named after the fifth element of ancient philosophy. Unlike the static vacuum energy, quintessence proposes a cosmic fluid that changes over time, its repulsive strength waxing or waning. Imagine pressing your hand into a bowl of syrup. The resistance varies with speed. Similarly, quintessence might have been weak during the universe's fiery youth, letting matter clump into galaxies, then strengthen to drive today's runaway expansion. Some models even suggest it could one day reverse, collapsing the cosmos in a big crunch. The implications are staggering. If vacuum energy dominates, the universe faces a big freeze, galaxies vanishing over the horizon until each is alone in an endless void. With quintessence, the outcome is wilder. It might eventually rip apart stars, planets, even spacetime itself in a big rip. Right now, telescopes like the Dark Energy Survey are mapping millions of galaxies to see which theory holds. Because dark energy isn't just a curiosity, it's the force that will decide how the universe dies. But what if dark matter doesn't exist at all? Enter Mordechai Milgram's radical idea, modified Newtonian dynamics, or MON. Forget invisible particles. This theory suggests we've simply misunderstood gravity itself. Picture a car accelerating on a highway. At high speeds, the engine roars, obeying familiar physics. But below a certain threshold, say, crawling through a school zone, the rules change. Milgram proposed something similar for gravity. In the weak gravitational fields at galaxy edges, Newton's laws tweak ever so slightly, eliminating the need for dark matter. The evidence is startling. MON predicts the rotation curves of hundreds of galaxies with eerie precision, matching observations better than dark matter models in some cases. Even stranger is the bullet cluster, two galaxies colliding, where visible matter and gravitational effects seemingly separate. Dark matter theorists cite this as proof of its existence, but MON supporters counter with tidal dwarf galaxies, where gravity behaves oddly in ways their equations anticipated. Yet critics pounce on MON's biggest weakness. It struggles to explain the cosmic web, the vast scaffolding of galaxy clusters stretching across the universe. Without dark matter's gravitational pull, how did such large-scale structures form so quickly after the Big Bang? Now shift gears entirely. What if gravity's quirks come from dimensions beyond our own? String theory proposes up to 11 dimensions, most curled into spaces tinier than an atom. Imagine ants crawling on a telephone wire. From afar, they seem to move in a straight line, unaware the wire's surface is a curled dimension. Similarly, gravity might leak into these hidden folds, explaining why it feels weaker than other forces. In some models, this leakage could mimic dark matter's effects without requiring new particles. The test: look for deviations in gravity over minuscule distances. Experiments like the Earth-Wash Group's exquisitely balanced torsion balances hunt for gravitational anomalies at widths thinner than a human hair. So far, Newton's law holds firm, but if it cracks, extra dimensions could rewrite the rules. Meanwhile, MON and string theory sit at a crossroads, one tweaking gravity's equations, the other weaving it into a multidimensional tapestry. Both remind us that the universe's greatest mysteries might not hinge on what we've missed, but on how boldly we're willing to rethink what we think we know. Now imagine this: every event unfolding in our three-dimensional world, every supernova explosion, every whispering galaxy, is actually encoded on a distant two-dimensional surface, like a cosmic DVD projecting the illusion of depth. This is the essence of the holographic principle, one of the most startling ideas in modern physics. The theory suggests that the universe might not be what it seems, that what we perceive as volume and space could be a grand illusion, a hologram etched onto the fabric of reality at its most fundamental level. The spark for this idea came from an unlikely place: black holes. In the 1970s, physicist Jacob Bekenstein made a startling observation. A black hole's entropy, a measure of its hidden information, wasn't proportional to its volume, as you might expect, but to its surface area. Picture a library where all the books are crammed onto the spines lining the shelves rather than filling the space inside. This odd connection hinted that the information swallowed by a black hole might be stored on its boundary, the event horizon, rather than being lost forever. Decades later, string theorist Juan Maldacena took this further with the AD/S/CFT correspondence. a mathematical bridge between two seemingly unrelated worlds. On one side, you have a warped, higher-dimensional space riddled with gravity like the space near a black hole. On the other, a flat, gravity-less surface governed by quantum rules. Maldacena showed that these two descriptions could be equivalent, like translating a novel into another language without losing the story's essence. Here's where it gets even stranger. If the math holds, our tangible, three-dimensional universe might be nothing more than a projection from a two-dimensional surface at its edge. An idea as unsettling as discovering the world outside your window is a painting on a faraway wall. Think of how a credit card's hologram shifts when you tilt it, creating the illusion of depth from flat, encoded data. Now scale that up to cosmic proportions. Every particle collision, every ripple of gravity, even the firing of neurons in your brain, might be data points shimmering on some unimaginably vast flat cosmic screen. Critics argue that testing such a theory seems impossible. How do you prove reality is an illusion? But recent experiments with quantum entanglement offer tantalizing clues. When particles remain mysteriously linked across vast distances, some physicists suggest this spooky action at a distance could be evidence of information encoded on a deeper, lower dimensional layer. Others are probing the fabric of spacetime itself, searching for pixelation or noise that might betray its holographic nature, like detecting the graininess of a photograph when blown up too large. Whether the holographic principle holds or not, it forces us to confront a radical possibility that the universe's deepest truths might not lie in the stars or galaxies we see, but in the invisible, information-rich boundaries we've barely begun to fathom. Reality, it seems, might be far stranger and far flatter than we ever dreamed. Even the grandest cosmic structures, those sprawling galaxy clusters stretching across billions of light years, owe their existence to the tiniest of beginnings. Rewind the universe to its first trillionth of a second, when space itself underwent an explosive growth spurt called inflation. In that fleeting moment, the entire cosmos ballooned from smaller than an atom to the size of a grapefruit, smoothing and stretching space-time to near-perfect flatness. But perfection wasn't quite achieved. At the quantum level, empty space wasn't empty, it crackled with microscopic fluctuations, particles and energy flickering unpredictably like static on a cosmic radio. As inflation stretched the universe, it didn't just magnify space, it magnified those quantum tremors, freezing them into the fabric of reality itself. These frozen ripples became the universe's architectural blueprints. Denser regions where fluctuations had packed extra energy exerted slightly stronger gravitational pulls, drawing in surrounding matter over billions of years. The result, galaxy clusters, filaments, and vast cosmic void structures that trace their lineage back to those quantum seeds. The evidence for this astonishing story is written across the oldest light we can see, the cosmic microwave background, or CMB. This afterglow of the Big Bang, now cooled to just a few degrees above absolute zero, bears faint temperature variations, hotter and colder spots no larger than 1 part in 100,000. Like shadows cast by infant quantum fluctuations, these patterns were first mapped in detail by satellites like Kobe and Planck, revealing a match so precise it feels like cosmic forensics. But here's the twist that bends the mind. The CMB's fluctuations aren't random noise, they follow a very specific pattern predicted by quantum physics during inflation. It's as if the universe left behind a fingerprint, and the ridges match the equations describing how quantum jitters get stretched across spacetime. Even more remarkably, the strength of these fluctuations hints at inflation's energy scale, suggesting the process was driven by a field so potent it makes the Large Hadron Collider look like a toy. Critics once argued that inflation was untestable, a just-so story for the universe's smoothness. But the CMB's statistical signatures, from the relative sizes of hot and cold spots to the way they're distributed, have turned inflation into one of cosmology's most robust frameworks. Alternate theories like cyclic universes or bouncing cosmologies struggle to replicate these exact patterns, yet puzzles remain. Why did inflation start or stop? Could multiple episodes have occurred, each imprinting its own layers of fluctuations? Future CMB experiments, like the Simons Observatory, aim to hunt for even fainter imprints, primordial gravitational waves that would reveal inflation's final, violent moments. What began as quantum static became the scaffolding for everything we see, a reminder that the universe's largest structures are at heart the amplified whispers of its smallest beginnings. And if we're reading those whispers right, they tell us that even the void isn't truly empty, it's a canvas where quantum uncertainty painted the stars. What if spacetime, the very stage on which the universe plays out, isn't a fixed backdrop at all, but something that emerges from deeper, weirder quantum connections? This is the wild promise of emergent spacetime, a theory that reimagines reality's fabric as a sort of cosmic mirage. At its heart lies a surprising ingredient, quantum entanglement, that spooky link where particles share instant connections regardless of distance. Einstein famously dismissed it as spooky action at a distance, but today, physicists suspect entanglement might be the thread stitching spacetime itself into existence. Take the AR equals EPR conjecture, a daring idea that bridges two of physics' most perplexing concepts. ER refers to Einstein-Rosen bridges, wormholes or tunnels through spacetime. EPR is the Einstein-Podolsky-Rosen paradox, highlighting entanglement's bizarre non-locality. In 2013, physicists Juan Maldacena and Leonard Susskind proposed these weren't just analogies but two faces of the same phenomenon. Imagine two entangled particles as the mouths of a microscopic wormhole. Though they're far apart in space, their quantum connection could literally be a shortcut through the geometry of spacetime itself. It's as if the universe's roads and highways, the distances we take for granted, are built from an invisible network of quantum handshakes. This reshapes how we think about black holes. When matter falls into one, it doesn't vanish, it leaves an imprint on the event horizon, a holographic record. Now picture two black holes entangled. Their interiors might be connected by a wormhole while their exteriors appear separate. This isn't just theory. Researchers have simulated such systems using quantum computers, watching how entangled qubits mimic wormhole dynamics. The implications ripple outward. If spacetime emerges from entanglement, then the smooth continuity we experience might be like the surface of a lake, calm and solid seeming, but fundamentally made of countless tiny interactions beneath. Critics argue this remains speculative, lacking direct experimental proof, but hints are mounting. In 2022, a team measured entanglement entropy, a proxy for quantum connections, in a lab-scale black hole analog, finding patterns that echo spacetime geometry. Others suggest that if entanglement builds spacetime, then severing it might make space itself fracture. That could explain why attempts to probe spacetime at ultra-tiny scales, like with quantum gravity experiments, hit a wall. There's no there, just a web of relations. The most radical take: if spacetime is emergent, then the Big Bang might not have been an explosion in space, but the birth of space from an underlying quantum network. It's a vision where the universe isn't happening inside spacetime, it is spacetime woven into being one entangled thread at a time. Neutrinos are the universe's ultimate escape artists, particles so elusive they can pass through a light year of lead without a single collision. Born in the cores of stars, the fury of supernova, and even the decay of atoms in your own body, these ghostly travelers barely interact with matter at all. Yet their very indifference to ordinary forces might be hiding something extraordinary. Whispers of a hidden sector of physics, a shadow realm where neutrinos dance to the tune of undiscovered weak forces. For decades, neutrino experiments have been plagued by strange mismatches between theory and observation. Take neutrino oscillations, the phenomenon where these particles shape-shift between three known types, electron, muon, and tau neutrinos. While scientists can predict how often these shifts should occur, real-world detectors consistently spot more electron neutrinos than expected. It's as if every time you counted cars passing through an intersection, a few extra mysteriously appeared from nowhere. One explanation: these missing neutrinos might be oscillating into a fourth, undetectable type, a sterile neutrino, invisible to our instruments because it interacts only via a force we've yet to discover. The idea isn't as far-fetched as it sounds. Our current standard model of physics only accounts for 3 neutrino types, but the math leaves room for more. Sterile neutrinos wouldn't feel the weak nuclear force which governs radioactive decay nor electromagnetism's pull. Instead, they might respond solely to a new, ultra-feeble interaction, a force so weak it's been hiding in plain sight. Imagine trying to hear a whisper in a hurricane. Until now, the storm of known particles drowned it out. Hints of this hidden force surfaced in the 1990s at the Los Alamos Liquid Scintillator Neutrino Detector (LSND). Here, muon antineutrinos seemed to vanish at higher rates than standard oscillation models allowed. Later, the Mini-Booni experiment at Fermilab saw similar anomalies, excess electron neutrinos flickering into existence where they shouldn't. Critics argue these could be calibration errors or unaccounted background noise. But if the pattern holds, it might point to sterile neutrinos with masses vastly different from their known cousins, oscillating under the influence of a new force's subtle tug. The stakes are immense. Discovering a fifth force, one acting exclusively on neutrinos, would shatter the standard model's tidy symmetry. It could explain why neutrinos have mass at all, a puzzle that's haunted physicists since their discovery. Even wilder, some theories suggest sterile neutrinos might be key to dark matter, their collective gravity shaping galaxies while their weak interactions keep them invisible. Others propose these particles are portals to a dark sector, a parallel universe of particles chatting only through forces alien to our own. Right now, experiments like Fermilab's ESBIAN program and Japan's J-PARC are hunting for definitive proof. They're tuning detectors to catch the faintest neutrino whispers, searching for oscillation patterns that defy conventional physics. Because if sterile neutrinos and their secret forces are real, they're not just rewriting the rules, they're revealing an entire shadow universe, one ghostly handshake at a time. Time crystals sound like something ripped from a sci-fi novel, materials that somehow move without energy, repeating their patterns not in space but in time itself. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who dared to ask, could there be a phase of matter that breaks time symmetry, just as ordinary crystals break spatial symmetry? Think of a diamond, its atoms arranged in a rigid lattice that repeats in space. A time crystal would do something similar, but instead of repeating in 3 dimensions, it would oscillate between states in a never-ending loop, like a clock that ticks forever without being wound. At first glance, this seems impossible. The laws of thermodynamics insist that perpetual motion machines can't exist. Any system not driven by external energy will eventually wind down. But time crystals don't violate these laws. They don't produce energy or motion from nothing. Instead, they exist in a quantum superposition, flipping between states in a cycle that doesn't require energy input. Imagine pushing a child on a swing just once and watching them rock back and forth forever without friction or decay. That's the essence of a time crystal. It finds a loophole in nature's rules, dancing in a rhythm locked to the fundamental ticking of the universe. The first experimental confirmation came in 2017, when teams at Harvard and the University of Maryland coaxed chains of ions or nitrogen vacancy centers in diamonds into this exotic state. Using lasers or microwave pulses to kick the systems periodically, they observed the atoms settling into a rhythmic pattern that repeated at a fraction of the driving frequency. It wasn't perpetual motion, it was quantum synchronization, a delicate balance where the system's lowest energy state still contained structured, repeating motion. What makes time crystals revolutionary isn't just their defiance of classical intuition, it's their potential. Quantum computers face a major hurdle: coherence. Qubits, the building blocks of quantum information, are notoriously fragile, their delicate states collapsing at the slightest disturbance. Time crystals, with their inherent stability and resistance to perturbations, could act as perfect quantum memory. Picture a vault where information isn't stored statically, but encoded in an indestructible rhythm, immune to external noise, but the implications go even deeper. Some theorists speculate that time crystals might offer clues about time's arrow, why we remember the past but not the future. Others wonder if they could mimic exotic phenomena like time loops, or even serve as components in future time-keeping devices far more precise than atomic clocks. For now, these possibilities hover at the edge of theory and experiment, a reminder that the most profound breakthroughs often begin as questions that sound, at first, like pure fantasy. For centuries, we've lived with the comforting certainty that nature operates under four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But what if there's a fifth hiding in plain sight? Enter the Yukawa force, a hypothetical interaction proposed to explain anomalies in subatomic behavior. Named after physicist Hideki Yukawa, who predicted the pion particle binding atomic nuclei, this fifth force would act over microscopic distances, weaker than electromagnetism but stronger than gravity. Picture two magnets on a table. At close range, they snap together, but step back and their pull fades. A Yukawa-type force would behave similarly, its influence dropping off exponentially with distance, like a whisper lost in a crowd. Some of the strongest hints come from radioactive decay experiments. When certain isotopes decay, they emit particles at energies that don't quite match predictions. One explanation, a fleeting, unknown boson, dubbed the X-boson mediating a new force, could be subtly altering the outcomes. Hungarian researchers in 2015 claimed to spot such anomalies in beryllium-8 decays, sparking a hunt for this elusive carrier. If confirmed, it wouldn't just add a fifth force to the ledger. It could bridge gaps in our understanding of dark matter, or even hint at supersymmetry, a theory pairing every known particle with a heavier twin. Now shift gears to an even stranger contender: chameleon particles. These hypothetical entities tied to dark energy take their name from their uncanny ability to change mass based on their surroundings. In dense environments like Earth's atmosphere, they'd be heavy and sluggish, barely interacting with matter. But in the emptiness of space, they'd become almost weightless, their repulsive effects amplifying to drive cosmic acceleration. It's as if these particles wear cosmic camouflage, blending into local conditions while invisibly shaping the universe's expansion. Testing for chameleons isn't easy, their very nature makes them evasive. But ingenious lab setups are trying. The EART-WASH group at the University of Washington uses finely balanced torsion balances to measure gravitational forces at micron scales. If chameleons exist, their subtle pushes should create detectable deviations from Newton's predictions. Meanwhile, particle accelerators like CERN are attempting to coax chameleons into revealing themselves through high-energy collisions, watching for unexpected energy signatures. What unites these two theories is their audacity. A fifth force challenges the completeness of our physical framework, while chameleon particles suggest dark energy might not be a uniform field, but a swarm of shape-shifting entities. Both remind us that the universe's deepest secrets might not lie in revising old theories, but in uncovering entirely new layers of reality. Black holes have long been cosmic paradoxes, objects so dense they trap light, yet their behavior threatens to unravel the very laws of physics. At the heart of this contradiction lies the information paradox, a puzzle so profound it pitted Stephen Hawking against the foundations of quantum mechanics. The trouble starts with Hawking radiation. The eerie glow black holes emit due to quantum effects near their event horizons. Pair by pair, particles and antiparticles flicker into existence at the edge of the abyss. Most annihilate instantly, but occasionally one falls in while the other escapes, stealing a tiny bit of the black hole's mass. Over eons, this process evaporates the black hole entirely. But here's the catch. According to Hawking's early calculations, the escaping radiation carries no information about the matter that formed the black hole. It's like burning a library and claiming the smoke contains no traces of the books, a violation of quantum theory's sacred rule that information can never be destroyed. This sparked decades of debate. If Hawking was right, the universe would have a fundamental amnesia, erasing the histories of swallowed stars and planets. But in 2004, Hawking himself reversed course, conceding that information might escape after all, though how remained unclear. Enter the firewall hypothesis, a radical fix proposed in 2012. Imagine approaching a black hole's event horizon, expecting to cross it smoothly as Einstein's equations predict. Instead, you hit a searing wall of high-energy particles, a boundary so violent it would vaporize you before you ever reached the interior. This firewall would encode information in its chaotic energy, preserving it in the radiation, but at the cost of violating relativity's principle that free-falling observers feel no extreme forces. Critics argue firewalls are overkill, like dynamiting a house to preserve its blueprint. Alternatives abound. One suggests black holes don't vanish completely but leave behind Planck-sized remnants, dense as the universe's first moments, hoarding information in their cores. Others propose holographic scramblers, where data isn't lost but gets chaotically encoded on the event horizon's surface, like shredding a document and scattering its pieces across a sphere, waiting to be reassembled by some future cosmic decoder. The stakes couldn't be higher. If Hawking radiation truly erases information, it undermines quantum mechanics' bedrock. If firewalls exist, they rewrite Einstein's vision of spacetime. Experiments may be impossible, but math offers clues. In 2019, physicists calculated that islands of spacetime could form inside black holes, preserving information without firewalls. Meanwhile, quantum gravity models like string theory suggest information might leak through higher dimensional backdoors, escaping in ways our three-dimensional intuition can't grasp. Whatever the answer, the paradox reminds us that black holes aren't just cosmic vacuum cleaners, they're laboratories for the universe's deepest laws, pushing us to question reality itself. What if everything around us, the stars, the laws of physics, even your own thoughts, are nothing more than lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that's moved from fringe philosophy to serious scientific debate thanks to one compelling argument, Nick Bostrom's trilemma. In 2003, the Oxford philosopher laid out three stark possibilities. Either civilizations like ours almost always go extinct before developing simulation technology, advanced societies lose interest in creating ancestor simulations, or we're almost certainly living in one right now. Every scenario feels unsettling, but the math behind the third option is surprisingly robust. If future civilizations could run billions of simulations of their ancestors, the number of simulated minds would dwarf biological ones. Statistically, the odds tilt heavily toward us being among the simulations, but could we ever find proof? Some researchers point to quantum mechanics' strangest quirks as potential glitches in the matrix. Take wave function collapse, the way particles exist in multiple states until measured, as if the universe is conserving processing power by only rendering details when observed. Or consider the speed of light, an ultimate limit that prevents distant parts of the simulation from needing to sync too precisely, like lag in an overloaded game engine. Even tiny inconsistencies in cosmic ray energies or mathematical constants could betray deeper layers of code. critics counter that these anomalies might just reflect our incomplete understanding of physics. Yet experiments like the search for pixelation in the cosmic microwave background evidence the universe has a finite resolution, shows scientists aren't dismissing the idea entirely. After all, if we're in a simulation, the creators could have left Easter eggs. The question isn't just whether we can prove we're simulated, it's whether we'd ever want to know. Because if the simulation hypothesis is true, reality as we know it might be the most elaborate game ever played. Magnets are everywhere, clinging to fridge doors, guiding compass needles, even humming inside your headphone. But every magnet you've ever encountered has a fundamental duality, a north pole and a south pole inseparably linked. Snap a bar magnet in half, and instead of isolating a single pole, you get two new magnets, each with its own pair of north and south ends. This symmetry is so ingrained in our understanding that James Clerk Maxwell's equations, the bedrock of classical electromagnetism, treat electric and magnetic fields as intertwined phenomena. Yet in 1931, physicist Paul Dirac tossed a theoretical grenade into this tidy framework. What if magnetic monopoles, particles carrying isolated north or south charges, actually exist? Dirac's math revealed something startling. If even one magnetic monopole lurked somewhere in the universe, it would explain why electric charge comes in discrete, quantized units. His equations showed that the existence of a monopole would force electric charge to be quantized, meaning particles could only carry multiples of a fundamental charge. This elegant connection between magnetism and electricity was too beautiful to ignore. Imagine a world where electric charge could take any value, where electrons might have a charge of 1.7 or 2.3 instead of exactly 1. It would throw atomic physics into chaos. Monopoles, Dirac argued, were nature's way of keeping the cosmic ledger balanced. The hunt for these elusive particles has taken physicists to some of the most extreme environments imaginable. When the early universe was a seething plasma of energy, conditions might have been perfect for monopoles to condense out of the chaos, like ice crystals forming in supercooled water. Particle accelerators like the Large Hadron Collider have scoured high-energy collisions for traces of them, while underground experiments monitor ancient minerals for fossilized monopoles that might have gotten trapped in Earth's crust billions of years ago. Even cosmic rays bombarding the Moon's surface have been scrutinized for hints of these magnetic loners. But why have we never found one? Some theories suggest monopoles are just too massive to be produced in modern particle colliders, relics of an era when the universe's energy density was unimaginably higher. Others propose they're hiding in plain sight, disguised as topological defects in spacetime's fabric. Picture the universe as a vast carpet. Monopoles could be like frayed threads where the weave twists in on itself, creating points of isolated magnetic charge. If that's true, spotting one might require rethinking how we search, not as particles but as cosmic knots. The implications of finding a monopole would ripple far beyond textbook revisions. Maxwell's equations would need a rewrite, and our understanding of symmetry in physics from the quantum scale to the cosmos would undergo a seismic shift. String theory, for instance, predicts monopoles as inevitable byproducts of higher dimensional physics. Their discovery could be the thread that finally ties together quantum mechanics and gravity. For now, the monopole remains a ghost in the equations, a tantalizing what if that keeps physicists scanning the skies and the data for a glimpse of magnetism's missing half. Deep in the equations of particle physics, there's a theory so bizarre it challenges our very understanding of what matter could be. It's called unparticle physics, a concept dreamed up by Harvard's Howard Georgi in 2007. And it proposes a shadow realm of stuff that doesn't behave like particles at all. Forget protons, neutrons, or even electrons. Unparticles are scale invariant, meaning they have no fixed mass or size. Picture a cloud of smoke, zoom in or out, and its wispy structure looks roughly the same. Unparticles share this eerie property, existing in a hazy state between defined forms, like cosmic chameleons that refuse to settle into traditional roles. What makes this idea more than just mathematical poetry? Dark matter's stubborn refusal to fit known categories. WIMP and actions might dominate the conversation, but their predicted signatures remain elusive. Unparticles offer a wild alternative. What if dark matter isn't made of particles in the usual sense, but of this enigmatic, scale-free substance? Its interactions with ordinary matter wouldn't follow the clean rules of particle physics. Instead of colliding like billiard balls, unparticles might smear across spacetime, producing faint, anomalous signals in detectors like gusts of wind you can't see but might feel as a chill. Jorge's breakthrough was realizing that certain high-energy theories could produce unparticles when a hidden sector of the universe becomes decoupled from ours. Imagine two parallel oceans separated by an invisible barrier. Waves in one don't directly ripple into the other, but their presence subtly warps the boundary. In this scenario, unparticles would mediate forces between the visible and hidden worlds, leaving fingerprints in phenomena like rare particle decays or gravitational anomalies. The hunt is already on. Physicists sift through data from the Large Hadron Collider for excess energy events, unexplained blips that could signal unparticle interactions. Others analyze neutron stars, where extreme gravity might squeeze unparticle effects into observable distortions. Even the cosmos' large-scale structure could hold clues. If unparticles tug on galaxies differently than traditional dark matter, their influence might be etched into the cosmic web's peculiar wrinkles. Critics argue unparticles are a mathematical sleight of hand, lacking direct experimental backing. But their allure lies in their sheer strangeness, a reminder that the universe's hidden layers might not just defy expectations, but dissolve the very framework we use to define them. Whether real or not, unparticle physics stretches our imagination, proving that the answers to dark matter's riddles might lie not in heavier particles, but in a reality where particle itself is just an approximation. Imagine our universe as just one page in an infinite cosmic book, a single three-dimensional brain, floating in a higher dimensional space. This is the essence of brain cosmology, a radical offshoot of string theory where our entire reality might be confined to a membrane or brain, drifting through a grander multidimensional bulk. Picture a soap bubble suspended in the air, its surface a perfect, self-contained world. Now imagine countless other bubbles hovering nearby, each with its own physics, its own stars, its own version of reality. According to this theory, the Big Bang wasn't the beginning of everything. It might have been the aftermath of a collision between our brain and another, a cosmic car crash that released enough energy to birth the universe we know. The implications are staggering. If brains exist, gravity could be the only force leaking into the bulk, explaining why it's so weak compared to other fundamental forces. Particles like electrons and quarks might be tethered to our brain like pins stuck in a corkboard, unable to venture beyond it. But here's where it gets stranger. If another brain drifted close enough, its gravity could tug on ours, creating bizarre effects like phantom galaxies or unexplained cosmic flows. Some theorists even suggest dark matter might be ordinary matter trapped on a neighboring brain, its gravity seeping through the dimensional divide like echoes through a wall. Now shift to the ekpyrotic universe, a twist on brain cosmology that trades a one-time Big Bang for an endless cycle of collisions. The name comes from the ancient Greek word for conflagration, and it paints a dramatic picture, our brain and a parallel one locked in an eternal dance, drawn together by invisible strings of energy, colliding, rebounding, and colliding again over trillions of years. Each collision reignites the universe in a fiery reset, scattering matter and energy anew. Unlike the classic Big Bang, which starts with a singularity of infinite density, ekpyrosis begins with a finite, calculable event, a slower, smoother process that sidesteps the need for a mysterious starting point. Critics argue these ideas are untestable, but subtle clues might lurk in the cosmic microwave background. A brain collision could leave imprints in the polarization patterns of ancient light, like ripples frozen in a pond. Others hunt for gravitational waves at frequencies too low for current detectors, relics of a pre-Big Bang clash. The math behind these theories is elegant, but the real challenge is bridging the gap between abstraction and observation. After all, if our universe is just one ripple in a higher dimensional ocean, how do we even begin to map the depths? Brain cosmology and the ekpyrotic model remind us that the universe's origin story might be far richer and far stranger than we ever imagined. Whether our reality is a solitary membrane or one thread in an endless cosmic tapestry, these theories push the boundaries of what's possible, daring us to rethink not just how the universe began, but how it might begin again. At the heart of a neutron star, where a sugar cube-sized chunk of matter weighs more than Mount Everest, the laws of physics start to break down in spectacular fashion. These cosmic corpses, born from the collapse of massive stars, squeeze protons and electrons together so violently that they merge into neutrons, creating the densest stable matter in the universe. But crush anything hard enough, and it'll reveal secrets no one saw coming. There's mounting evidence that deep within neutron stars, the unimaginable pressure may be triggering a phase transition far stranger than anything in our textbooks, a transformation where neutrons themselves dissolve into a seething ocean of free-floating quarks and gluons, the building blocks of all nuclear matter. This primordial soup, called quark-gluon plasma, normally only exists fleetingly in particle colliders or in the universe's first microseconds after the Big Bang. But in neutron star cores, it might persist as a bizarre, ultra-dense state nicknamed strange matter. Here's why that's revolutionary. Quarks come in 6 flavors, and under everyday conditions, they're always paired or tripled, like up and down quarks binding to form protons and neutrons. But in this extreme environment, the rules change. The immense pressure could destabilize ordinary matter, allowing strange quarks, a heavier, exotic variety, to dominate. If that happens, the entire star might undergo a metamorphosis, crystallizing into a single, continent-sized nucleus of pure strange matter. The implications are staggering. Strange matter would be what physicists call more stable than ordinary matter, meaning that if it exists, it could be contagious. A single droplet touching Earth might catalyze our planet's atoms into converting, rewriting our very chemistry in a chain reaction. Before you panic, know this: we've likely been bathed in neutron star debris for billions of years without catastrophe, suggesting either strange matter is rarer than thought, or that it doesn't behave as feared. Detecting these quantum alchemy labs isn't easy, but astronomers have 2 clever approaches. First, they listen for starquakes, glitches in neutron stars' otherwise perfect rotation. A solid crust floating atop a liquid quark core would crack like tectonic plates, releasing gravitational waves with a very specific fingerprint. Second, they measure stars' sizes. A quark core makes neutron stars slightly squishier, altering how much they bend spacetime when paired in binary systems. Recent data from NASA and NICER telescope hints at stars too large to be pure neutrons, yet too small for conventional models, a Goldilocks zone where quark cores might hide. The ultimate test, a neutron-star collision. When 2 of these dense orbs spiral together and merge, their interiors briefly experience pressures rivaling the Big Bang. Simulations show quark matter would delay the resulting gamma ray burst by milliseconds, a blink that observatories like LIGO and Fermi could spot. In 2017, such a collision was detected, but the data remains inconclusive. Future upgrades to gravitational wave detectors might finally catch this smoking gun, proving that the universe's most extreme objects are also its most revolutionary physics labs. What makes this theory so thrilling isn't just its audacity, It's the possibility that neutron stars aren't dead ends, but cosmic crucibles forging matter into forms we've yet to imagine. If confirmed, strange matter wouldn't just rewrite nuclear physics. It would reveal that the universe, even in its darkest corners, is still playing with recipes we've barely begun to taste. Every time you open your eyes, the world seems solid, stable, a single, definite reality you can rely on. But zoom into the quantum level and that certainty dissolves. Particles exist in multiple states at once, a blur of possibilities known as superposition. So why don't we see chairs or trees in two places simultaneously? The answer might lie in a revolutionary idea called quantum Darwinism, a theory that explains how the fuzzy quantum world picks which version of reality we actually experience. At its core, quantum Darwinism suggests our classical reality isn't just randomly chosen, it's selected through a kind of cosmic survival of the fittest. Here's how it works. When a quantum system interacts with its environment, whether it's a photon bouncing off an atom or a dust grain jostling in the air, countless tiny interactions measure the system in slightly different ways. But not all quantum states survive this bombardment. Some configurations are more resilient, capable of imprinting themselves onto the environment repeatedly, like a song played so often it becomes unforgettable. These preferred states become the ones we observe, while the fragile, more exotic possibilities fade away, drowned out by the noise of the universe. Think of it like footprints in wet sand. A single step leaves a faint mark, easily washed away by the tide. But walk the same path 1,000 times and you carve a deep, permanent trail. In quantum Darwinism, the environment acts like that tidal force, erasing delicate quantum superpositions while reinforcing stable, classical outcomes. This isn't just philosophy, it's math. Physicists have shown that pointer states, the quantum configurations least disturbed by environmental noise, align perfectly with the familiar, definite properties we see in everyday objects like position or momentum. The eerie part, this means reality as we know it isn't universal, it's negotiated. A solitary atom in deep space might linger in superposition indefinitely, untouched by decoherence. But here on Earth, where particles are constantly jostled by air molecules, light, and even cosmic rays, quantum weirdness gets shredded almost instantly. Experiments with tiny objects like buckyballs molecules made of 60 carbon atoms show this in action. Isolated in a vacuum, they exhibit wave-like interference. But expose them to even a whisper of gas, and they collapse into classical particles, their quantum behavior erased by environmental chatter. Critics argue quantum Darwinism merely shifts the mystery rather than solving it. After all, who or what decides which states are fit enough to survive? Yet supporters counter that it's the first theory to explain why certain outcomes dominate without invoking conscious observers or hidden variables. It turns the measurement problem, quantum physics' greatest puzzle, into a question of durability. The most observable states are simply the ones that endure long enough to be observed. The implications ripple far beyond labs and equations. If quantum Darwinism holds, it suggests reality isn't handed down from some fundamental law. It emerges from trillions of tiny interactions, a consensus reached by the universe itself. And that raises a haunting possibility. What we perceive as objective might just be the loudest echo in a symphony of infinite quantum whispers. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cycle of cosmic rebirth? That's the bold vision of Sir Roger Penrose's conformal cyclic cosmology, a theory where universes don't just end, they transform. Picture this: as our universe expands toward heat death, all matter eventually dissolves into massless particles like photons, stretching spacetime into an infinite, featureless void. But here's Penrose's twist. In this ultra-smooth state, the universe loses any sense of scale. A galaxy and an atom become indistinguishable mathematically. Time and distance cease to have meaning, and in that moment, the dying universe's geometry becomes identical to the hot, dense singularity of a new Big Bang. The cycle resets not with a bang or a whimper, but with a cosmic sigh. This isn't just poetic symmetry, it's rigorous math. Penrose's model relies on conformal rescaling, a geometric trick that lets you stretch or shrink spacetime while preserving angles. Imagine a deflated balloon covered in dots. Blow it up and the dots spread apart, but their geometric relationships stay the same. Now imagine the balloon expands forever until the dots are infinitely distant, yet mathematically, their configuration remains identical to the uninflated state. That's how CCC bridges eons. When our universe's far future becomes geometrically equivalent to a new universe's beginning, the cycle begins anew without violating physics. But could we ever find proof of past universes? Penrose points to eerie anomalies in the cosmic microwave background, circular patterns dubbed Hawking points, named after his late collaborator Stephen Hawking. These faint rings, he argues, are the imprints of supermassive black holes from a previous eon, their final explosions etched onto the CMB like cosmic fingerprints. Critics dismiss these patterns as statistical noise, but Penrose's team claims they align too precisely with CCC's predictions. If real, these ghostly circles would be the ultimate cold case, evidence of a universe that existed before time as we know it began. The implications are staggering. CCC sidesteps the need for cosmic inflation, replacing it with an eternal loop where black holes, often seen as destroyers, become the seeds of new creation. It also redefines entropy's role. Instead of driving the universe toward disorder, entropy resets at each conformal boundary, allowing information to cross between cycles in coded form. Picture a library where every book is pulped at closing time, only for its words to magically rearrange into new stories at dawn, yet challenges remain. Mainstream cosmology questions how quantum states could persist across eons, and why dark energy's acceleration fits so neatly into CCC's framework. But Penrose's vision dares us to rethink not just how the universe began, but whether beginning even makes sense in an endless cosmic Ouroboros. After all, if time is cyclical, then every ending might just be a prelude written in the geometry of nothingness. Einstein-Rosen bridges, better known as wormholes, have long been dismissed as mathematical curiosities, tunnels through space-time so unstable they'd snap shut faster than light could traverse them. But what if these cosmic shortcuts aren't just science fiction? Modern physics is uncovering a startling connection between wormholes and quantum teleportation, revealing that the two might be different faces of the same fundamental phenomenon. At first glance, they couldn't seem more different. One warps the fabric of the universe, while the other links particles across vast distances without any physical bridge. Yet the math binding them is eerily identical. Take quantum entanglement, where particles become mysteriously linked regardless of distance. Change the spin of one electron here, and its entangled partner light years away instantly mirrors that change. No signal, no delay, just perfect synchronization. Einstein called this spooky action at a distance, but in 2013, physicists Juan Maldacena and Leonard Susskind proposed something even spookier. Entangled particles might actually be connected by microscopic wormholes, their quantum link a physical tunnel through spacetime's hidden geometry. It's as if the universe, faced with the paradox of faster-than-light influence, cheated by bending the rules, not breaking them. The evidence lies in the equations. In holographic models of the universe, the same math describing quantum teleportation also describes particles traversing wormholes. The key is information. When you teleport a quantum state, you're not sending matter, just the data needed to reconstruct it elsewhere. Similarly, a wormhole could act as a cosmic fax machine, transmitting information from one point to another through a warped space-time conduit. The catch: both processes rely on entanglement. Without it, teleportation fails, and according to Maldacner's ER=EPR conjecture, so would the wormhole. Experiments are already teasing out this bizarre link. In 2022, researchers used a quantum computer to simulate a pair of entangled black holes, the holographic equivalents of wormholes. By manipulating the qubits, they watched information seemingly teleport between them, mirroring how matter might traverse a theoretical Einstein-Rosen bridge. The simulation was crude, a shadow of the real thing, but the logic held. Entanglement and wormholes obey the same rules because in some deep way they might be the same thing. This blurs the line between quantum weirdness and cosmic structure. If every entangled pair is joined by a Planck-scale wormhole, then spacetime itself could be woven from countless invisible threads, a vast network of shortcuts stitching the universe together. Some theories even suggest that traversable wormholes might be engineered by amplifying quantum entanglement, though the energy required would dwarf anything humanity could muster. But the implications go beyond engineering. If ER=EPR holds, it would mean that quantum mechanics and gravity, the two pillars of modern physics, aren't just compatible but fundamentally intertwined, each a reflection of the other in a mirror we're only beginning to glimpse. Critics argue that these ideas, while elegant, remain untested outside simulations. Yet as quantum computers grow more sophisticated, they might recreate increasingly complex spacetime geometries, probing whether entanglement truly builds the universe's hidden scaffolding. The dream, a unified theory where black holes, wormholes, and quantum teleportation all emerge from the same cosmic code, a reality where the strangest phenomena are just different expressions of one deeper truth. For now, the bridge between Einstein's relativity and quantum spookiness remains theoretical, but each equation nudges us closer to a revelation. The universe might not just contain wormholes. It might be made of them. In the quest to unite all fundamental forces under one grand cosmic rulebook, physicists stumbled upon a mathematical symphony so elegant it seemed too good to ignore supersymmetry, or SUSY for short. This theory proposes that every particle we've ever discovered has a hidden twin, a sparticle, lurking just beyond our current observational reach. It's as if the universe is running a cosmic version of mirror matching, where electrons have selectron partners, quarks pair with squarks, and even the Higgs boson might shake hands with a Higgsino. The beauty of this symmetry isn't just aesthetic. It solves some of physics' thorniest puzzles in one stroke. For starters, it elegantly bridges the chasm between gravity and quantum mechanics by suggesting these sparticles could mediate forces we've yet to detect. Even more compelling, SUSY offers a perfect candidate for dark matter. The lightest sparticle, stable and invisible, drifting through the cosmos like a ghostly anchor. Yet here's the cosmic tease. Despite decades of searching, not a single sparticle has shown up in the Large Hadron Collider's ultra-precise detectors. The LHC has smashed protons together at energies that should have conjured these shadowy twins into existence, yet the data remains stubbornly silent. Critics argue this silence is a death knell for supersymmetry, but supporters counter with a twist: what if sparticles are far heavier than originally predicted? SUSY doesn't demand they appear at any specific energy. It only insists they must exist somewhere in the universe's ledger. The LHC's limits have pushed theorists to rethink their models, imagining scenarios where sparticles are cloaked in higher energy realms, awaiting colliders more powerful than anything we've built. Meanwhile, another layer of mystery deepens the plot. If sparticles are too elusive, could dark matter instead be composed of entirely different shadow particles, entities outside SUSY framework? Enter hidden sector theories, proposing a whole zoo of particles interacting solely through a secret force, like whispers in a language ordinary matter can't hear. Experiments like the CERN NA64 and Fermilab's Dark Quest are hunting these phantoms by blasting beams into walls of heavy metal, watching for missing energy that might betray a hidden particle's flight. The stakes couldn't be higher. discovering sparticles would crown SUSY as the keystone of a unified physics. Finding shadow particles instead could rewrite the rules entirely, revealing a parallel universe of matter playing by its own clandestine laws. For now, the equations hum with possibilities, the colliders keep probing, and the universe guards its secrets closely. Whether supersymmetries, elegant twins, or shadow particles from uncharted realms eventually step into the light, one thing is clear: the answers won't just fill textbooks, they'll redefine reality's blueprint. Deep beneath the equations of particle physics lies a ticking time bomb, a theory so unsettling it could rewrite the very fabric of reality in an instant. It's called vacuum decay, and the trigger might be hiding in plain sight within the Higgs field, the same quantum entity that gives particles their mass. Right now, the universe exists in what scientists call a false vacuum, a state that seems stable, like a marble resting in a shallow bowl. But there's a terrifying possibility. That bowl might actually be perched on the edge of a much steeper drop. If the Higgs field were to suddenly shift to its true, lowest energy state, it could unleash a cascading wave of destruction, rewriting the laws of physics at the speed of light. Picture a domino effect on a cosmic scale. A single quantum fluctuation, random energy bubbling up from the void, could nucleate a microscopic bubble of true vacuum. This bubble would expand in all directions, its walls racing outward faster than light. Inside, fundamental constants like the speed of light or the strength of gravity could take on entirely new values. Atoms might disintegrate, chemistry as we know it could vanish, and the very structure of spacetime might unravel. The worst part, you'd never see it coming. By the time the bubble's wall reached you, the physics enabling your brain to process the event would already be gone. How real is this threat? The math is sobering. Measurements of the Higgs boson's mass suggest our vacuum might indeed be metastable, persistent, but not perfectly secure. Think of it like an ice cube teetering on a table's edge. It could stay there for billions of years, or a random vibration could send it crashing down tomorrow. The universe has already lasted 14 billion years without collapsing, which might sound reassuring until you realize that on a quantum timescale, we're still playing cosmic roulette. Some physicists argue that vacuum decay could already be underway somewhere in the cosmos, its deadly bubble racing toward us undetectably. Others counter that the Higgs field might be more stable than calculations suggest, or that unknown physics could prevent such a catastrophe altogether. String theory, for instance, posits countless universes with different vacuum states. Ours might just be one survivor in a graveyard of less fortunate realities. Yet the sheer audacity of this scenario forces us to confront a humbling truth. The universe isn't just stranger than we imagine, it might be far more fragile. Every second we exist, we're essentially gambling that the deepest layers of reality won't suddenly flip the table. And while the odds seem slim, the stakes couldn't be higher. After all, in the face of vacuum decay, not even the laws of physics are guaranteed to last. At scales trillions of times smaller than an atom, where space and time lose their familiar smoothness, reality might dissolve into a seething chaos called quantum foam. This isn't just poetic imagery, it's the heart of non-commutative geometry, a radical theory suggesting spacetime itself has a granular structure, like the pixels on a screen too fine for any microscope to see. Imagine zooming in on the surface of a still pond until the water's calm facade breaks apart into frenzied droplets. At the Planck scale, distances of 10 to the power of -35 meters. The universe might behave similarly, with spacetime churning in a turbulent dance of virtual black holes and wormholes flickering in and out of existence too quickly to measure. What makes this idea more than wild speculation? The math behind it reveals something startling. At these extreme scales, the very concept of here and there breaks down. In ordinary geometry, distances commute, meaning measuring from point A to B gives the same result as B to A. But in this quantum realm, the order of measurements matters profoundly, like trying to navigate a city where streets rearrange themselves depending on which way you face. The coordinates of spacetime become non-commutative, governed by equations where x times y doesn't equal y times x. This isn't just abstract algebra, it's a clue that beneath reality's smooth surface lies a frothing, probabilistic sea where position and momentum blur into uncertainty. The implications ripple outward. If spacetime has this foamy texture, it could explain why gravity resists unification with quantum mechanics. Einstein's theory treats spacetime as a continuous fabric, but what if that fabric is woven from indivisible threads that vibrate and twist unpredictably? Some models suggest these quantum fluctuations might even leave detectable signatures, subtle distortions in light from distant gamma-ray bursts as high-energy photons punch through the foam's turbulence. Experiments like the Fermi Gamma-Ray Space Telescope have hunted for these telltale delays, though results remain inconclusive. Critics argue that without direct evidence, quantum foam remains speculative. Yet its allure lies in how elegantly it resolves paradoxes. Take black hole information loss. If spacetime is fundamentally granular, information swallowed by a singularity might be preserved in the foam's churn, like a message scrambled but not destroyed. Even the Big Bang singularity could dissolve into a quantum fluctuation within this primordial froth, sidestepping the need for a beginning altogether. The most mind-bending possibility, quantum foam might not just underlie reality, it could enable it. Some theorists propose that particles themselves are knots or vibrations in this turbulent spacetime, meaning the universe isn't made of things moving through space, but of space itself knitting matter into existence. It's a vision where the stage and the actors are one and the same, where the answers to physics' greatest mysteries might lie not in particles or forces, but in the hidden geometry of nothingness. What if spacetime isn't smooth and continuous, but stitched together from tiny, shifting geometric fragments like a cosmic quilt pieced from four-dimensional triangles? That's the startling premise of causal dynamical triangulation, a theory that reimagines the fabric of reality as a dynamic mosaic of spacetime atoms. Picture a child's toy set where triangular tiles snap together to form complex shapes, but instead of plastic, these tiles are elementary building blocks of existence itself, each one a tiny, quantum-scale chunk of spacetime with its own causality, its own arrow of time. At the heart of this idea is a radical approach to quantum gravity. Most theories treat spacetime as a backdrop, a static stage where particles perform. But CDT flips the script, suggesting spacetime emerges from the collective behavior of these triangulated pieces. Imagine throwing a handful of confetti into the air individually. Each scrap is meaningless, but viewed from afar, they trace the shape of a soaring bird. Similarly, in CDT, the universe's four-dimensional geometry isn't fundamental, it's what bubbles up when countless spacetime triangles interact under strict causal rules. The magic lies in how these triangles evolve. Unlike random quantum foam, CDT imposes order. Each triangle must connect to others in a way that preserves causality, ensuring time always moves forward, never backward or in loops. It's like building a house where every brick must align with the blueprint of cause and effect. Computer simulations reveal something astonishing. When these causal triangles self-assemble, they spontaneously generate a four-dimensional universe resembling ours, complete with familiar large-scale geometry. At microscopic scales, spacetime appears wildly fluctuating, but zoom out, and it smooths into the cosmos we recognize. Critics argue this approach is too rigid, potentially missing quantum gravity's full complexity. Yet CDT offers tangible solutions to long-standing puzzles. For one, it naturally avoids the pathological infinities plaguing other theories, no singularities, no spacetime tears. It also hints at an explanation for dark energy. The tiny gaps and stresses between triangulated pieces could accumulate into a repulsive force on cosmic scales. Most provocatively, CDT suggests time itself might be an illusion, a statistical artifact emerging from the causal network's pattern, much like temperature emerges from atomic motion. The implications spiral outward. If spacetime is truly built this way, then black holes might be regions where the triangulation phrase and the Big Bang could mark the moment this quantum assembly first locked into coherence. Future experiments probing Planck-scale physics, like ultra-precise measurements of gravitational waves, might detect subtle spacetime graininess, offering clues. For now, CDT stands as a bold reminder that the universe's deepest truths might not lie in particles or fields, but in the geometry of connection itself, a cosmic puzzle where every triangle holds a piece of reality's blueprint. Long before the first galaxies flickered to life, the universe may have hosted monsters beyond comprehension. Stars so colossal they bypassed supernovas entirely, collapsing straight into black holes like cosmic trapdoors snapping shut. These weren't just any stars. Theorists call them black hole stars, celestial leviathans hundreds of times more massive than our Sun, burning furiously in the cosmic dawn. Picture a furnace so vast its core gravity overwhelms even the explosive force of nuclear fusion, where the star's own weight crushes it into oblivion without the usual fireworks. These primordial behemoths could hold the key to one of astronomy's greatest mysteries: how supermassive black holes, those billion solar mass giants anchoring galaxies, appeared so shockingly early in cosmic history. The math behind black hole stars reads like something from mythology. In the universe's first 100 million years, before heavy elements polluted the primordial gas clouds, conditions were ripe for these giants to form. Without elements like carbon or oxygen to cool and fragment the collapsing gas, clouds could amass staggering volumes of hydrogen and helium, condensing into stars with masses reaching up to 1 million suns. Their lives would be brief and violent. A typical star balances gravity's inward pull with the outward pressure of fusion, but above a certain threshold, around 260 solar masses, radiation pressure can't compensate. The core becomes unstable, buckling under its own weight in a matter of millennia, sometimes even centuries. The result, a direct collapse black hole, born not from a dying star's collapse, but from a living one's surrender. What makes this theory so compelling are the fingerprints left behind. Supermassive black holes detected in the early universe, like the 800 million solar mass behemoth powering the quasar J1342 plus 0928, simply shouldn't have had time to grow so large through conventional accretion. But seed them with 1,000 solar mass black holes from these primordial stars, and the timeline snaps into place. It's like finding a sequoia sapling in a freshly planted forest. Unless something extraordinary jump-started its growth, its size defies explanation. Simulations reveal even wilder possibilities. Some black hole stars might have undergone quasi-stable phases, their cores oscillating between collapse and partial rebound, swallowing surrounding matter in violent pulses. Others could have formed in dense clusters, their gravitational dance leading to mergers that birthed intermediate mass black holes, missing links in the cosmic food chain. The echoes of these events might still linger. Future gravitational wave detectors could catch the ripples from such ancient collisions, while telescopes like JWST hunt for the chemical signatures of their surroundings. Stars this massive would have ionized their neighborhoods with ultraviolet radiation, leaving behind bubbles of helium-rich gas as cosmic breadcrumbs. Critics argue that direct observational proof remains elusive, but the mere possibility reshapes our understanding of cosmic dawn. If black hole stars existed, they weren't just oddities. They were the universe's first architects, forging the gravitational wells around which galaxies would later crystallize. Their legacy might be written in the very structure of reality, hidden in the depths of every supermassive black hole's shadow. Dark matter pulls galaxies together, while dark energy flings them apart, two invisible forces locked in a cosmic tug of war. But what if these opposing phenomena are actually two faces of the same mysterious substance? This is the radical premise behind dark fluid theory, a proposal that unifies the universe's greatest enigmas into one exotic medium with properties so bizarre they defy common intuition. Imagine a cosmic chameleon that behaves like an adhesive in some contexts and a repellent in others, its identity shifting based on the environment. That's the essence of dark fluid, a single entity masquerading as two. The key lies in negative mass, a concept that sounds ripped from science fiction. Ordinary matter always has positive mass responding to gravity's pull. But negative mass would do the opposite, push away when pulled, creating anti-gravitational effects. Dark fluid theory suggests this exotic substance could explain both dark matter's clumping and dark energy's repulsion. Picture squeezing a balloon filled with dark fluid. The regions under pressure act like attractive dark matter, while the stretched areas exert repulsive dark energy effects. One substance, two behaviors, unified under the same mathematical framework. Critics initially dismissed negative mass as unphysical, but recent simulations show startling consistency with observations. When programmed into cosmological models, dark fluid naturally forms halos around galaxies, mimicking dark matter's scaffolding, while simultaneously driving accelerated expansion on cosmic scales. The math even predicts subtle density fluctuations that could explain why galaxy rotations don't always align with standard dark matter predictions. Some researchers argue this flexibility makes dark fluid more elegant than separate dark sector theories. It solves two puzzles with one equation. Yet mysteries remain. Negative mass implies bizarre phenomena like runaway motion, where a dark fluid particle chased by another would accelerate endlessly, violating energy conservation. Proponents counter that dark fluid might only exhibit effective negative mass in specific regimes, like how ice behaves differently than liquid water despite being the same substance. Others suggest the fluid could be a quantum vacuum effect, with its apparent negative mass arising from complex interactions in spacetime's underlying structure. The hunt for evidence is underway. If dark fluid exists, its unusual gravitational signatures might be detectable through subtle distortions in galaxy clusters or anomalies in the cosmic microwave background. Upcoming telescopes like the Vera Rubin Observatory could spot telltale gaps in the distribution of galaxy motions, places where dark fluid's dual nature leaves an imprint. Whether confirmed or not, this theory challenges us to rethink the universe's hidden layers not as separate puzzles, but as interconnected threads in a far weirder tapestry. At the quantum level, particles exist in a haze of probabilities, a blur of potential states that only snap into focus when measured. But what if this collapse into reality isn't just triggered by detectors or lab equipment, but by something far more intimate, human consciousness itself? This is the spine-tingling premise of the von Neumann-Wigner interpretation, a fringe but mathematically rigorous take on quantum mechanics that dares to place the observer's mind at the center of the cosmic stage. The idea traces back to the early days of quantum theory. John von Neumann, a titan of mathematical physics, demonstrated that the boundary between the quantum system and the measuring device is arbitrary. There's no clear point where superposition collapses into a definite state. His collaborator, Eugene Wigner, took this further, proposing that conscious awareness might be the only true collapse mechanism. Picture a photon traveling through a double-slit experiment. According to Wigner, it's not the photographic plate or the scientist's equipment that forces it to choose a path, but the moment the scientist's mind registers the result. The universe, in this view, is like a vast quantum soup simmering with possibilities until a conscious observer crystallizes one into reality. Skeptics bristle at this, and for good reason. Mainstream quantum theory avoids invoking consciousness, favoring decoherence, the idea that interactions with the environment destroy quantum states coherence long before human awareness enters the picture. A dust grain jostled by air molecules doesn't need a mind to force it into a classical state. The universe does that automatically, yet Wigner's camp counters with intriguing edge cases. Take quantum experiments, delayed choice, or quantum eraser setups, where an observer's decision to measure or not seems to retroactively alter a particle's past behavior. It's as if the universe holds its breath until someone looks. The debate intensifies when you consider Wigner's friend, a thought experiment highlighting the paradox. Imagine a scientist in a lab measuring a quantum system, while another scientist outside waits to hear the result. For the first scientist, the quantum state collapses upon measurement. But for the second, the entire lab, including the first scientist's mind, remains in superposition until they're told the outcome. Who's right? Both perspectives are mathematically consistent, exposing a bizarre relativity of reality itself. Critics argue this veers dangerously close to solipsism, where the universe hinges on individual perception. But proponents clarify, they're not claiming humans magically control reality, only that consciousness plays an irreducible role in the quantum classical transition. Some even speculate that advanced AI or alien minds could serve the same function. Any sufficiently complex information processing system might count as an observer. Others, like physicist Roger Penrose, blend this with neuroscience, suggesting quantum processes in brain microtubules could bridge mind and quantum physics. The stakes are as profound as they get. If consciousness truly shapes reality, it blurs the line between physics and philosophy, challenging the very notion of an objective universe. Laboratories are now probing these ideas with increasingly sophisticated quantum cognition experiments, testing whether human decision-making exhibits subtle quantum-like probabilities. Whether the von Neumann-Wigner interpretation holds or not, it forces us to confront a humbling possibility that in the quantum theater, the observer might not just be in the audience, they could be writing the script. Most cosmic doomsdays play out over eons: black holes evaporating, stars burning out, galaxies drifting apart. But phantom energy offers a far more dramatic finale, a cataclysm so violent it could shred spacetime itself in a final, blinding instant. This nightmare scenario hinges on a single, eerie possibility: that dark energy's repulsive force isn't just constant but growing stronger over time. Current observations peg dark energy's equation of state parameter, denoted as W, at close to -1. But if that value dips even slightly below, say, W equals -1.01, the universe's fate takes a dark turn. Phantom energy, as this hypothetical substance is called, would cause the expansion of space to accelerate exponentially, not just steadily. Imagine stretching a rubber band slowly at first, then faster and faster until it snaps. Now replace the band with the fabric of reality. Within this scenario, phantom energy's grip tightens mercilessly. First, galaxy clusters will be torn apart as the space between them expands faster than light can bridge the gap. Next, individual galaxies unravel, their stars flung into the void like sparks from a bonfire. But the true horror comes in the final minutes. As the expansion rate approaches infinity, planetary systems disintegrate. Then planets, then molecules. In the last fraction of a second, atomic nuclei, the last bastions of structure, are ripped apart by the runaway stretching of space itself. The universe doesn't just fade into darkness, it dissolves into a featureless sea of disconnected particles, each forever isolated beyond the reach of any force. Observational data, for now, offers a sliver of hope. Measurements of supernova, baryon acoustic oscillations, and the cosmic microwave background constrain W to a range that barely skirts the phantom zone. The Planck satellite's latest readings suggest W equals -1.03 plus or -0.03, a result still consistent with the safer cosmological constant. But the margin of error leaves room for unease. Should future telescopes like the Vera Rubin Observatory or ESA's Euclid mission detect even a slight tilt toward W less than -1, the countdown to a big rip could theoretically begin. Yet here's the twist. Some theorists argue phantom energy might self-destruct before reaching its apocalyptic climax. Quantum effects near the Planck scale could destabilize it, causing a phase transition that halts the acceleration like a match burning out before igniting a powder keg. Others propose that phantom energy's rise might trigger new physics, warping spacetime into higher dimensions that bleed off the excess repulsion. It's a cosmic irony. The very mechanism that could doom reality might also contain the seeds of its own undoing. Whether phantom energy remains a mathematical curiosity or a looming threat hinges on the next generation of sky surveys. Because if the universe's expansion has a hidden accelerator pedal, we'll want to spot it before the brakes become impossible to find. Forget everything you know about particles, the tiny, point-like dots we imagine as the building blocks of matter. What if electrons, quarks, even photons aren't objects at all, but ripples on an invisible cosmic drumhead? This is the neutron wave universe theory, a vision so radical it dissolves the standard model's menagerie of particles into something far more elegant, standing waves vibrating through a hidden higher dimensional medium. Picture plucking a guitar string. The vibrations create distinct notes, each with its own frequency. Now imagine those notes aren't sound but matter itself. An electron might be one harmonic, a quark another, all resonating in a dimension we can't perceive. The roots of this idea stretch back to the 1920s, when physicists like Louis de Broglie first suggested particles might have wave-like properties. But the neutron wave universe takes it further, proposing that what we call particles are merely the peaks and troughs of waves trapped in a compactified higher dimensional space. Think of it like ocean waves crashing against a cliff. From a distance, each wave looks like a distinct thing, but up close, you see they're just water moving through a larger medium. In this theory, spacetime isn't the static stage of relativity. It's a dynamic, vibrating membrane where waves interact to create the illusion of solidity. Why does this matter? For starters, it could solve quantum mechanics' weirdest quirks. Take entanglement. If two particles are really just excitations of the same underlying wave field, their instant connection across distances makes intuitive sense, like two boys bobbing in sync on the same pond. Even the uncertainty principle clicks into place. A wave's position and momentum are inherently fuzzy. The math gets wilder when you add extra dimensions. String theory imagines tiny, curled-up dimensions, but here, those dimensions might host standing waves whose harmonics dictate particle properties, an electron's mass and charge. Just artifacts of its vibrational mode. Critics argue this sounds more like philosophy than physics, whereas the experimental proof, yet tantalizing hints exist. When scientists fire neutrons through crystals, they diffract like waves, not particles. Some quantum gravity models even predict higher dimensional wave resonances that could manifest as unexpected particle masses or forces. Future colliders might spot anomalies in energy distributions that betray this hidden symphony. The boldest implication: if the neutron wave universe is real, then the search for fundamental particles is a mirage. There's nothing to find, just harmonies to decode, vibrations to map. It's a universe where matter isn't the script, but the echo of something deeper, a cosmic vibration waiting to be heard. Deep beneath the Black Hills of South Dakota, shielded by a mile of rock from cosmic interference, the LUX Zeppelin experiment is hunting for shadows in the dark. This isn't just another detector, it's the most sensitive dark matter search ever built. A 5-ton vat of ultra-pure liquid xenon chilled to -100 degrees Celsius. The setup is deceptively simple. If a hypothetical WIMP, a weakly interacting massive particle, glides through the tank, it might, just might, bump into a xenon nucleus, producing a flash of light and a ripple of free electrons. Scientists have spent a decade refining this system, eliminating background noise to the point where even a single rogue electron from natural radioactivity could spoil the hunt. But here's the twist: the quieter the detector, the louder the cosmic whispers become. LUX Zeppelin null results aren't failures. They're carving away swaths of theoretical territory, ruling out entire classes of dark matter candidates with each passing month. Meanwhile, across the globe, an entirely different kind of experiment is listening to the universe's heartbeat. Pulsar timing arrays, networks of radio telescopes tracking the precise spins of dead stars, have become gravitational wave microscopes. These millisecond pulsars are nature's most accurate clocks, their beams sweeping past Earth with metronomic regularity. But when a gravitational wave stretches space-time as it passes, it subtly alters the pulse's arrival times, like a record skipping on a cosmic turntable. The North American Nanohertz Observatory for Gravitational Waves, NanoGrav, recently hit pay dirt, a low-frequency hum permeating the cosmos, likely the combined rumble of supermassive black hole binaries circling each other in distant galaxies. This isn't just about detecting waves, it's about mapping the gravitational landscape of the universe, revealing collisions too vast and slow for LIGO to catch. But what about the quantum realm? In labs from Boulder to Heidelberg, physicists are exploiting Bose-Einstein condensates, clouds of atoms cooled to near absolute zero, to probe spacetime's fuzzy underbelly. At these temperatures, atoms lose their individuality, merging into a single quantum wave function that's exquisitely sensitive to minute forces. By manipulating these condensates with lasers, researchers can simulate conditions near black holes or even test hypotheses about quantum gravity. One audacious experiment at the University of California, Berkeley, aims to detect spacetime's hypothetical granularity by observing how ultra-cold atoms scatter. If spacetime is truly pixelated at the Planck scale, the atom's behavior should betray subtle deviations from smooth quantum mechanics, like a ball rolling over sand instead of glass. Each of these experiments, LUX Zeppelin patient watch, pulsar arrays celestial metronomes, and condensates quantum ballet, represents a frontier where theory meets the unforgiving scrutiny of reality. They're not just answering questions, they're teaching us how to ask better ones, because in the hunt for the universe's deepest secrets, sometimes the most profound discoveries begin by listening to what isn't there. These theories don't just rewrite the rules of physics, they collapse the very foundations of how we perceive reality. Einstein once mused, reality is merely an illusion, albeit a very persistent one, and today's breakthroughs suggest he might have been more right than he knew. Take quantum mechanics, where particles exist in multiple states until observed. Does this mean the universe remains undecided until a conscious mind forces its hand? Or consider the holographic principle, which reduces our three-dimensional world to a two-dimensional projection. If true, the solidity of your hand, the weight of a star, all of it could be a cosmic sleight of hand, a trick of information encoded on a distant surface. Renowned physicist Niels Bohr captured this upheaval when he said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." The shock isn't just technical, it's existential. If entanglement links particles across galaxies instantly, what does that say about the illusion of separation? If spacetime emerges from quantum connections, is distance itself a mirage? Philosophers and physicists alike grapple with these questions, straddling the line between science and metaphysics. Carlo Rovelli, a leading voice in quantum gravity, frames it starkly. We are not stuff that persists. We are patterns, processes, knots in a web of relations. Even time, that most relentless of constants, isn't spared. In loop quantum gravity, time disappears from the fundamental equations, a phantom emerging only at larger scales. Julian Barber, a physicist who argues time is an illusion, puts it bluntly: the universe isn't in time, it creates time. Imagine a universe where cause and effect aren't dictated by a flowing river of moments, but by a vast, unchanging block where past, present, and future coexist. It's a vision that would make even Einstein pause, one where free will, memory, and the arrow of time itself are up for debate. Dark matter and dark energy deepen the existential vertigo. We've built our understanding of reality on the 5% of the cosmos we can see, like analyzing an elephant by studying its tail. As astrophysicist Katie Mack notes, we're not just in the dark about dark matter, we're in the dark about most of the universe. The humbling truth: our models of existence might be as incomplete as a map drawn by medieval sailors, with entire continents of reality still labeled, "Here be dragons." And then there's the simulation hypothesis, which reduces centuries of human inquiry to a cosmic game of The Sims. If we're living in an advanced civilization simulation, as Nick Bostrom's trilemma suggests, does that make our struggles less real or more terrifyingly arbitrary? Theoretical physicist Lisa Randall counters with a different kind of awe. The universe doesn't owe us meaning, we create it. Whether we're stardust, strings, or lines of code, the act of questioning might be the only authenticity we need. The philosopher-scientist Erwin Schrödinger once wrote, "The world is given to me only once, not one existing and one perceived." Today's theories dissolve that dichotomy, merging observer and observed into a dance of mutual creation. They challenge us to live with uncertainty, to find wonder not in answers but in the vast, glittering unknown. After all, if reality is a story we're still learning to read, the next page could change everything. After journeying through 30 mind-bending theories, from dark matter's invisible scaffolding to quantum foam's pixelated spacetime, one truth becomes painfully clear: the universe laughs at our certainty. Every answer uncovers deeper questions, every discovery reveals vaster mysteries. We've mapped the cosmic microwave background, weighed galaxies, and split atoms, yet 95% of reality remains hidden in shadows. The more we learn, the more we grasp how little we truly know. Consider the contradictions we've uncovered. Dark energy stretches the cosmos apart while dark matter clumps it together. Quantum particles defy logic by existing in multiple states until observed, while relativity insists time slows under gravity's grip. Even the vacuum of space isn't empty, it's a seething quantum froth where particles flicker in and out of existence. These aren't flaws in our understanding, they're signposts pointing toward physics we've yet to imagine. The humbling beauty of these theories isn't just in their complexity, it's in their audacity. They dare to propose that black holes might encode universes, that our reality could be a hologram, or that consciousness itself might stitch the quantum world into being. Some ideas will inevitably prove wrong, but their value lies in how they stretch the boundaries of the possible. As physicist Richard Feynman once quipped, "Science is the belief in the ignorance of experts." Yet this ignorance isn't despair, it's liberation. Each unanswered question is an invitation to explore, each paradox a door to new worlds. When Carl Sagan whispered, "We are a way for the cosmos to know itself," he captured the profound irony of our existence, tiny, fleeting creatures on a pale blue dot, gifted with just enough insight to sense the vastness of our own incomprehension. So tell us, which theories shattered your perception of reality? Was it the chilling prospect of vacuum decay, where physics itself could rewrite in an instant? The haunting elegance of Penrose's cyclic cosmology, where universes rebirth in geometric echoes? Or perhaps the neutron wave universe, where particles dissolve into vibrational harmonies? Drop your favorites in the comments and let's keep the conversation cosmic. Because the greatest lesson of all, the universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's what makes the search so